Hello everyone, I'm İpek Küçükkaya. I'm an undergraduate student at Bilkent University in the physics department. In this video, I will be showing you the footage of the experiment that I conducted in the physics lab for the course of Waves and Optics. This experiment is about laser Doppler velocimetry, in which the flow speed of the liquid can be found by using the Doppler frequency effect. This can be found because frequency shift is proportional to the velocity of the particle in the flow direction. When the light scatters off a moving particle instead of emitting directly from the light source, this Doppler effect can be observed. We tried this experiment by using aluminum particles flowing in water, and the laser beams will scatter by these particles. We used a laser, a beam splitter, a mirror, a converging lens, a water pump, and some aluminum particles. We also used a photodiode on a breadboard setup and an Arduino Uno to get signals and then transfer them to MATLAB on a computer. A beam splitter was put in front of the laser with 45 degrees angle. Then, near the beam splitter, a mirror was put with a 60 degrees angle. We measured these angles by using a protractor. When the laser was turned on, the beam passed through the beam splitter. Then, the beam split into two beams. One of these two beams went straight through the beam splitter. The second beam reflected to the mirror. After the second beam reflected from the mirror, these beams intersected at a point. This point is also called the measuring volume. Doppler shift will take place at the measuring volume. We constructed a rectangular prism by cutting 4 rectangular pieces by using Viva couple SR sheet. After cutting them, we used a silicone adhesive gun to connect all these pieces together. Then, 2 square pieces were also cut to close the open parts of the rectangular prism. By using a soldering iron, circular holes were cut on these square pieces. We arranged the water pump's hose so that it will enter one of these holes to provide water into the rectangular prism. We put a water bottle to keep the aluminum particles in the water, and we also used a glass bottle to collect the exiting water. Water hoses were connected to the water pump and rectangular prism. Here you can see our rectangular prism. We constructed the breadboard circuit with connecting cables, signal amplifier, 10,000 ohm resistor, 100 nanofarad capacitor, photodiode, and some jumper cables. MATLAB and Arduino code scripts were used to measure signals, Doppler frequency shift, and light intensity. We put all the setup together and put the rectangular prism on the measuring volume. We put a converging lens after the rectangular prism to focus the two beams at another point. The other intersection point will be the place where the photodiode will be placed. In this footage, you can see the experiment. Water is coming from the water bottle to the rectangular prism. The two beams are intersecting in the rectangular prism, which is called the measuring volume. We now wait for the computer to plot the signals in MATLAB. We use a fast Fourier transform, FFT, in our experiment, which is used for filtering the discrete signals and obtaining a certain frequency. With many trial and errors, we finally recorded the signal with beat frequency, which is the frequency difference between two lasers. We kept seeing a peak of 30 Hz in the magnitude frequency graph, where FFT was applied when there was no disturbance in the system. This is the frequency difference between the two laser beams, which is the beat frequency. When there is a disturbance in the system, particles are moving, so there is a Doppler frequency shift observed. In the magnitude frequency graph, there is small peak seen near 10,000 Hz. This is the frequency difference of the two beams caused by the Doppler effect. We use the following equation for finding the velocity component of the particle in the x direction parallel to the direction of the flow, which is also the flow speed of the liquid. It is found as 0.01 meter per second or 1 centimeter per second. It is physically meaningful for a particle to go 1 centimeter in the rectangular prism in 1 second in the flow direction. In the equation, Ft is the frequency shift caused by the Doppler effect. Theta is taken as the angle between the two beams, and the wavelength is taken as the green laser's wavelength. We had some errors due to turbulence. Not all the frequency shifts were the same, and not all of them were 10,000 Hz. That is why we don't see any huge peak at 10,000 Hz. We just see smaller peaks very close to each other. The potential improvements are making a flawless rectangular prism that doesn't leak any water, or using a stronger pump or a laser that may be found in advanced laboratories. We could also try making the perfect alignment in an optics laboratory. All in all, this experiment has been a scientific way to experience laser Doppler velocimetry and Doppler effect by using optical setup.